decomposing into two normal form, we are getting a very right or decomposition, we are getting the proper decomposition, and you can test that, you can test it by whatever data values are there, you can put those data values accordingly, project them into the new tables, and you will find on taking the join of these three relations on various attributes which are combining the two, you will find that you will get the same original relation. Okay. As far as dependencies are concerned, you will find that all those dependencies are being preserved. What do I mean by dependencies are being preserved? You will see this particular, that is name to phone dependency, name to major dependency is being preserved into the first relation. Course to, that is name and course to grid is being preserved into the second relation which we have designed, decomposed relation, as well as course to professor is being preserved into the third relation. So this is the way we have designed the proper form of this particular database. But is it the end of the story? So does we conclude that by two normal form the whole theory of normalization finishes or completes, or there are still more problems? Well, for the time being, for this particular example which we have taken, probably the problems are over. Okay, but this may not be in general the case. What kind of cases which may exist? Let us consider the relation which is given in the graphics. Well, visualize the relation, the roll numbers, the name, department, year, and hostel. Once again, a student database. For a person whose name is Raman, physics, etc., the data is there. He is in the first year and he is allocated to a hostel called Ganga. Okay. Similarly, he is in the second year, he has been allocated Kaveri. Third year, Krishna. Fourth year, Godavari. Well, this highlights some point. Roll number uniquely identifies, or roll number functionally determines the name. Roll number functionally determines the department. Roll number functionally determines the year as well as hostel. So that's perfectly okay. Okay. That means the given relation should be in 2NF. There is no problem. 2NF, as we said in the earlier case, there were no problems in the 2NF relation. But is there any additional constraint we can see in this particular state? Well, in the graphics, if what we were pointing out, that if you are in the first year, you are in Ganga hostel. If you are in the second year, you are in the Kaveri hostel. In the third year, you are getting Krishna. In the fourth, Godavari. That means something. A non-key attribute here can determine which hostel the students will be residing. That means there is a dependence existing between the year as well as the hostel. To visualize it, let us look into the dependency diagram. Now, dependency diagram states there is a link or there is a functional dependence from year to the hostel. If that is so, we are in trouble. Why we are in trouble? As you have found in the table, in the diagram which I had shown to you, wherever we are having one Ganga, it is being repeated. Ganga is being repeated. Whereas, if I simply say one, it should be sufficient to say that he will be residing in Ganga. There are inconsistencies. Not inconsistencies, there are redundancies, and obviously it is going to lead to the problems relating to insertion anomalies and deletion anomalies. To avoid such kinds of things, what we need to say, we need to go to third normal form. What is third normal form? The third normal form is defined to be that a relation should be in 2NF and all attributes in a relation scheme are functionally dependent only on the key. So what constraint we are adding here? We are adding one more constraint here, and that is that it should be only dependent on the key attributes, and then only it will be 3NF. Obviously, we are moving from 2 to 3NF for the reasons, once again, that is anomalies, that is insertion and deletion, and data redundancy problem. In 3NF, what kind of a decomposition will I get? Obviously, what I would like to break year as well as hostel into a separate relation, whereas roll number, name, department and year will be kept in another relation, and that is going to eliminate the problem which is associated with this particular table. So in 3NF, what we are trying to do? We are trying to eliminate any attribute that is non-key attribute related functional dependence. So you can see functional dependence is one of the prime factor which is responsible for this particular decompositions. But is BCNF that is 3NF sufficient, or we still have to move further? Well, 3NF to certain extent may be sufficient. However, a more rigid and defined form for 3NF happens to be BCNF. And in BCNF, the basic assumptions are that the relation has more than one composite candidate keys having one common attribute, and if there is such case, then if not common attributes of one composite key is dependent on an attribute of other composite key, a normalization called BCNF is needed. So what we are saying, in 3NF we are removing some problem, that is non-prime or non-prime attribute related problem, but the problem can exist because of prime attributes also. That is, if we have two candidate keys, one is a part of, that is non-overlapping part of those candidate keys is functionally determining the other part. Since they are not falling into the that is prime attributes, then you are going to encounter that these particular relations are in 3NF, okay, but they are not going to be in BCNF. Let us explain it with the help of an example where we are visualizing a professor database, where professor code, department, head of department and present time is there. Now, some of the basic assumptions which are listed happen to be a professor can work in more than one department, okay. The percentage time he spends in each department is known and is defined, and each department has only one head of department. So these are some of the constraints which we are defining. If these are the constraints, obviously all these constraints we would like to represent with the help of a dependency diagram. Now the dependency diagram is what we should like to see here. The department, the whole key. Now these onto the left hand side which you are seeing here, these are all key attributes, although there are two candidate keys. The first candidate key is department and professor number, and the second candidate key is professor number and HOD. Okay. If we consider department and professor number, they uniquely define the percentage time. If we consider professor number as well as HOD, they also uniquely define the percentage time attribute. But in addition, what we are having is a dependence at this point of time. That is, if I know a department, I know who is the HOD. In a sense, department functionally determines the head of the department. If that is so, we are going to fall into some problem. What is going to be the problem? Once again, you will see wherever, okay, so a professor may be occurring at various places, okay, he may be in 2 departments, 3 departments, okay, and there will be many professors in those departments. In all those places, in this particular relation, we are going to find redundancy of information as far as department and HOD fields are concerned. They are going to be repeated. Obviously, one of these fields should be kept, but you are going to, both the fields are going to lead to redundancy. And obviously, this is once again going to lead to the problem of insertion anomaly and deletion anomaly. And once again, what we have to do is decomposition. And this is what the decomposition happens to be. Professor code, department, and percentage time is kept into one relation. And we separate out department and HOD. So by this particular decomposition, what we are basically trying to ensure that our relation is in BCNF and we are divided, or we are not having the problems associated with redundancy, insertion anomaly, as well as deletion anomaly. So we have reached to a state where we say, okay, the relation is in BCNF. But does it exhaust all possible combination of realistic or industrial situation? Probably we have some more examples to see. One such example happens to be the example of a course relation. The course relation, for simplification, we are just considering three attributes: course, teacher, and text. Okay. What we are assuming here is that a course can be taught by many teachers, okay, and the teacher can teach multiple courses. That's slightly different issue right now, but whosoever teaches a course has to use specified number of text, irrespective of whosoever is or whatever teacher is teaching that particular course. In this particular case, the information which we would like to represent in this particular table basically is, so we have given an example of just two courses. Suppose I want to represent information CST 203. The two teachers are happening to be date and court, and the two texts which are to be taught in this particular course are happening to be file organization and relational design. CST 103, we have Sahani, who is teaching this particular course, and he is also teaching file organization and trees. This kind of overlap in text is possible among different courses. That kind of a thing does exist in a real life situation. Now, how would I like to represent this information into the tabular form? Well, I have to represent this information as shown in the diagram. That is, for date, for each text, okay, for each teacher, I need to represent. For example, CST 203 is being taught by date, okay, is being represented with two tuples and not one tuple. Here what we have to do is that CST 203 date file organization. So the information is like this: course CST 203 is being taught by date and he is teaching the text file organization. CST 203 is being taught by date and he has also to teach relational design. Similarly, two tuples are there for court. Similarly, two tuples are there for Sahani. Okay? As many texts are going to be there, as many tuples are necessarily to be entered. If we don't enter them, then the possible implication of the information may be, for example, if I don't enter that date with relational design, okay, that CST 203 date is teaching relational design. If I don't enter this particular tuple, there can be misinformation that date is just teaching the file organization. Okay, so this particular misinformation we cannot give. What we are trying to say here is we have the same problems once again. Okay, the FD's constraints, there is no FD in this particular relation. Why there is no FD? You will find that the whole, that is course, teacher, as well as text, all of them combined together forms the key. So if these are the three the attributes of, or the key, the prime attributes, then there is no chance of having any functional dependence into this particular relation. If there is no functional dependence, obviously this particular relation is in BCNF, yet it has the problem of redundancy of information. Why the problem is occurring here? The problem is occurring because of the independent nature of teacher as well as text. So what we would like to do, our common sense says that I would like to decompose this particular relation into a form called fourth normal form, okay, and the two relations which should exist here should be course and teacher, okay. A course defining various teacher, I can uniquely represent the information, and course and text, okay. So by this I can decompose the relation. What is the basic theory behind this particular decomposition? The basic theory for this particular decomposition happens to be defined as multi-valued dependencies, and that multi-valued dependencies is the prime factor for defining or using fourth normal form in a relational scheme. What is a multi-valued dependence? We have given just examples of it. If I say course multi-determines teacher, that is if and only if the set of teacher value matching a given course text pair values depends on only course and not the text values. The independence which I was talking about, that is, if I know the course, there are multiple teachers who are teaching it which are independent of the text which are there, okay. So this is what this particular statement means, okay. And the second statement which is there is that course multi-determines teacher also implies that course multi-determines text should also apply in the given relation. So what we have is these kinds of dependencies, and on that basis the decomposition as I had proposed has to take place. That is, we are going to decompose the relation into course teacher and course text. But is it complete? No, we still have one more problem probably. Now, how that particular problem can be visualized is a situation. Let's consider a vendor supplying many items to project in an organization. Now, what are the constraints in that? A vendor can supply many items, a project can use many items, and a vendor can supply to many projects. An item may be supplied by many vendors. If that is the situation, what we are visualizing here is a case where all these attributes, that is the vendor, the items which he supplies, and the projects, they are independent of each other. Once again, in this particular case, what we are going to find that since they are independent of each other, they will not be in any sense being controlled by each other. Therefore, joining these, the key will be consisting of vendor code, item code, as well as project code. Okay, so the composite of these three things will be the key. There is no functional dependence, so the relation is in BCNF. There is no NVD also existing in this particular relation, therefore it is in 4NF2. However, if I want to decompose this particular relation into 4NF, into two tables, okay, after all, what is the problem in this particular table? Once again, the same problem. If I want to represent the information that this vendor supplied this particular item, okay, and if he is not supplying that item to any of the projects, then this information cannot be represented in the table shown in the diagram. Okay, I cannot represent that V3 is supplying item I1, okay, to P2. In fact, there is a duplication that must be treated as a mistake. There is a duplication of information. Just one of these tuples is going to remain. The two tuples are not going to be there. But visualize it. V3 is supplying item I1 to project P2. Vendor V2 is supplying item I3 to project P1. But suppose he is not supplying it to project P1, then once again we are going to encounter the similar kinds of anomalies that is we had encountered earlier. Obviously, we would like to break it into two tables, okay? But those two tables, which we can, after all, this is not NVDs there. So obviously, those two tables, which we would like to design here, are happening to be vendor code, item code table, and vendor code project number table. However, what we find on taking the join of these two tables, the original table we will not be able to make. This is what you have to experiment. So if you are not able to make the original table, what is the solution? So under the circumstances, what is to be done in this particular case? Obviously, we would like to see that this particular table is not too decomposable, and this particular problem can be refined or can be implemented, okay, using 3 decomposability nature of these particular table. That is, instead of 2 tables, if we can break this particular relation into 3 tables by representing the third piece of information, that is, that which item is needed or used in which project, if we can provide that information also in another table, probably we are doing the proper justice to this particular table. These kinds of the normalization is called 5NF, okay, and 5NF is basically based on something called join dependency. That is, on taking the join of the 3 table, I'll get the original table. On taking join of the 2 table, I will not get the original table, and that is a problem. So we have broken this particular relation into 3 tables. Okay, so that tells us about the 5th normal form. Now let us summarize what we have done as far as normalization is concerned. In normalizations, all relations, if I want to a non-normalized relation, if I want to convert it to 1NF, I have to eliminate variable length records, multi-attribute records, okay. If I want to convert 1NF relation to 2NF, I have to remove dependency of non-key attributes on part of a multi-attribute key, okay. If I want to convert 2NF to 3NF, I have to remove dependency on non-key attributes on other non-key attributes. If I want to convert it into 4NF, or in fact 3NF to BCNF, then I have to see the removal of dependencies on attribute of a that is, whenever we have multi-attribute key, that if there is overlapping onto the non-overlapping portion, there shouldn't be any redundancy or any dependency. In 4NF, what we try to remove is multi-valued dependencies. So if I remove all the multi-valued dependencies from a relation, I will bring my relation to 4NF. And finally, to convert a relation into 5NF, I need to check whether a given relation is a 2 decomposable or it requires more relations which can be joined together to bring the original relation. In practice, you will find that this 5NF is not very commonly used. However, you will find that there are practical instances existing for 4NF as well as 5NF situations. The other part which you would like to see here is the query processing. What I will request you, you must try to experiment with lots of queries. You may take exemplar queries from the references books which we have suggested to you, and try to experiment with some of the queries, try to design your own queries, and that will give you tremendous confidence as far as query optimization is concerned. In fact, query optimization will come as a next step if you have designed your queries properly. You must try to, you should try to solve many queries using join and other similar kinds of concept which you have learned in block 1 as well as block 2. With this, I would like to end this particular session here. Bye, and thank you for listening to me.